So we've talked a little bit about the basic quantities. Really where we're trying to go with this is to use the model of conservation of momentum. Now, conservation of momentum is going to be something that we go into a little bit of detail. The book is exploring where it comes from. And really, I'm not going to go into the math there. You can refer to the book to get the details of the math. But the important idea is that during the interaction, the forces each of these objects exert on one another must be equal. That we know that from Newton's third law, that that's a law, that's always true, that's not some sort of simplification or approximation. So because the forces that these two objects exert on each other are equal and opposite, and we said that a force is related to a change in momentum, this means that the way your momentums change of each object are equal and opposite. So what we get to say is if you take both of your initial momenta and add them up, that's going to be equal to your final momenta. That isn't to say that your initial momentum of one object is equal to the final momentum of that same object, but when you consider everything happening in your system, final sum equals initial sum. So now note here that there's a lot of subscripts, that we have the x subscript because this is happening in one dimension. A later video is going to talk about how to deal with momentum in two dimensions. So in many one-dimensional problems, if you really only have one dimension, you could drop this x, but if you have a two-dimensional problem, you need to keep it there. You then have final f, initial I, and then you have a 1 and a 2 for object 1 and object 2. So please be careful with the notation. I don't necessarily care if you have the parentheses there or not, or if you change the order up, but make sure that you're not just writing PF or P1 because we actually need to know if it's final or initial, object 1 or object 2. So also note here that even though these are the same size, we're not making the assumption that they're the same mass. We're also not making the assumption that the velocities here are equal. So this is true in general, and we can even generalize it a little bit more, but where this idea is coming from is again these interaction forces and Newton's third law. So let's do a quick application of conservation of momentum. And in this case, we have two colliding train cars. This first car is at rest, the second car is at rest, the first car is moving with some initial speed. And for simplification in this problem, we're going to say that they have the same mass, but that isn't necessarily true. They collide and stick together, and now they're both traveling to the right. So how would we actually figure this out? If we don't know the details of the forces involved, we can't use forces. And we don't necessarily know what's going on with energy in this case. It's not actually true that energy is conserved here. And one of the ways that you can think about this is that there's something causing them to stick together. And so that actually can change the energy. So this is where we need momentum. We can't use forces to figure this out. We can't use energy to figure this out. So what we can say is that we have our initial momentum, each of these summed together equals our final momentum, each of these summed together. So this is our starting point equation. It's true whenever we have two objects interacting together. We then plug in some values, remembering that momentum equals mass times velocity. We said that the masses of each of these are just m, so that simplifies, and this one was initially at rest, so that's 0. Note that because these stick together, they're both traveling at vf, so I plug vf in for both of these. The momentum of this term is 0, and I can cancel m from each side. I'm then left with an equation that lets me relate vf to v initial. Because v initial must equal 2vf, we then can say that our final velocity is equal to half of our initial velocity. Now that's not a general result. In this case, we've assumed that this object is at rest and that the masses are equal, but we see that they stick together and then they're now rolling forwards more slowly at half the speed. So this is how we use conservation of energy. We can generalize it a little bit more to include all of the objects in our system. And we've met systems before already now with forces and energy. So once again, we need to define what is a part of our system and then what is external, what is the environment. And so we have some external forces potentially, I'll address that on the next soon, but then we also have these internal forces between all of the objects in our system. And so previously, the conservation of energy idea just used 2, but that can expand to be more than that. So we define total momentum with capital P. So be careful here. So this, capital P, I usually write the bar on the bottom, is total momentum or system momentum. If you want to then include the momentum of an individual object, that's where we use lowercase p, and we would, for instance, use 1, or again, depending on what you want to do, you might say initial x 1. But so the idea of system momentum or total momentum, same idea, is that you add up the momentum of every single object in your system. And so we could have the initial system momentum, final system momentum. So obviously your final system momentum is the sum of all of your initial momentums. Your initial system momentum is the sum of all of your initial momentums. Your final system momentum is the sum of all your final momentum. And here I'm just using 1, 2, 3, assuming that there's only 3 objects in my system, but there could be as many objects as I want. Also note that in this case, I haven't written x because I've left these as vectors. So make sure that you remember that you're doing vector addition here unless you break it out into individual components, such as each of these being x. You still would need to keep track of the signs in that case. So where this becomes useful is when we're dealing with isolated systems. And we've already met isolated systems when thinking about forces and when thinking about energy. So an isolated system has no external forces. We then get to say that our initial system momentum, this is capital P, is equal to our final system momentum. And this is really what we're talking about when we're talking about conservation of momentum. But that's only true if it's an isolated system. If you have a non-isolated system, then you could have a change in your system momentum that relates to your external forces. So in general, you want to make sure that you have an isolated system so that you don't need to worry about this. As before, what's important is how you define your system. And we've already seen this, especially for energy. So if our system is only a ball, then we see that we're changing its momentum due to the forces. But if in fact we define our system to be the ball and the earth, momentum is conserved then, but you're thinking about the momentum of both the ball and the earth. So normally we're not going to worry about conservation of momentum for a ball, but we might think about it for carts interacting or multiple balls interacting. So do think about what your system is, and ideally make sure that all of your interactions within the impulse approximation, remember that we normally get to ignore gravity, make sure that that's defined in your system so that your system is isolated. If you think you have to worry about an external force, you either want to redefine your system, define it differently, or think about whether or not you can use the impulse approximation. So in general now, what is our strategy? First, clearly define your system. This needs to be the first step with when you're making your models and you're drawing your representations. Ideally, you want to choose a system that's isolated so that there's no net forces from the external environment on your system. Or, note that there's an or here, the second scenario is when you get to ignore the external forces because the internal interactions are sufficiently short and large, impulse approximation. So those are the two things that we need to worry about, and if either of them is true, then we get to say that momentum is conserved. And that's the whole point of using this strategy. If you don't think you can do that, then break it into parts and use conservation of energy for only part of it. That's going to be really common. So when you define your model, make sure that you are clearly explaining what parts of the model are relevant for which pieces of the motion. Conservation of energy might only be valid for part of the motion. Draw your before and after pictorial representation. If there are multiple parts of the motion, you want a before and after for each part. As always, define your variables, list your values, etc. And then we get to use our conservation of momentum. Now here we're doing it in component form, x and y, and I'll talk about 2D conservation of momentum soon. But you want to make sure that you have the momentum of every single piece. So please use careful notation to make that clear, because you don't just get to say this for 1 or 2 pieces of your system. You have to include every single piece of your system here.